So the first of all, I would like to show you this different microscopes. You can able to see here, we have in our physical metallurgy lab, optical microscope here. And we have, this is scanning electron microscope, which is there in our central research facility. These are not the original images, but still this looks like this. And we have another microscope called transmission electron microscope. So basically we have optical microscope, we have electron microscope. This one and this one are electron microscope. Optical microscope means exactly we are using optical source of light, visible light, normal. We are using that. And we know that the wavelength of ordinary light is not so less, right? So that is why the resolution, we cannot resolve many things by using optical microscope, right? And the magnification also, we cannot go much beyond a particular limit, right? So that is the limitation of this optical microscope. You cannot resolve to a large extent, and you cannot magnify to a large extent. The image will appear as blur, right? Or you'll be showing like defocusing will be there. But in this case, we are using electrons. Here also we are using electrons. And we understand electrons means it has very short wavelength. So once it has very short wavelength and we are using electrons to view the images or the structures, so we can go for very high magnification and we can go for high resolution also. We can resolve the substance which are very closely spaced into one another. If two substances are very closely placed, we can resolve them easily. That this is one substance, this is another substance, this is another substance, like that. We can resolve them easily, which cannot be done by this one. And magnification, we can go for very high magnification. It depends upon the voltage, right? Because we have to use voltage to accelerate the electrons, right? How fast the electron will move, and we can see the things. So here we can see what is the motivation to this topic. The motivation to this topic is what we can able to see under a microscope. What we can able to see under a microscope. So microscope is a tool. It is an engineering tool, you can understand, right? Engineering tool or instrument by which we can able to see many microstructures or nanostructures. The size of the substance which are like 10 to the minus 6 meters or 10 to the minus 9 meters. You can imagine very fine substance, very small substance can be visible with the help of this microscope. So, and after getting the things like what kind of microstructures, what kind of nanostructures are present in our materials. Basically, I'm talking about our crystalline materials because we are dealing with metals, we are dealing with alloys, we are dealing with ceramics basically, right? So all are crystalline material basically. So with the help of this instrument microscope, we can able to see very small substances which are present in the materials, like microstructures or nanostructures. So basically nanostructures can be visible by help of this one and this one, most by this one. If a particle size is nano level, we can able to see them. Even we can able to see atoms if we are using a high HRTM, high resolution transmission electron microscope also. Anyways, so now we are moving to the next important part, that is by using an optical microscope, what we can able to see. Suppose you have a steel, right? You do sample preparation before putting the steel under a microscope, right? You already know those things. You need to do polishing, you need to do sectioning, then mounting, then polishing, then finally fine polishing, then at the end you will do etching. After doing etching, you have to put the sample under a microscope, right? So after putting the sample under a microscope, what we can able to see? We can able to see grains, right? We can able to see grain boundaries. We can able to see phases, if many phases will be there or a single phase will be there, right? We can able to see porosity if it is present. It is okay. So these are the things you can able to see under an optical microscope, right? Similarly, if you are using a scanning electron microscope, you can able to see grain, again, grains. It depends upon magnification, right? Grains, you can see grain boundaries, different phases if present. We can able to see fracture surface. If already a surface has been fractured, we can able to see, identify which kind of fracture has taken place, that is ductile or brittle. We can able to see big size precipitates. Precipitate means here the second phases. Second phases. But that should be a bigger size somewhat. Similarly, what kind of things we can able to see under a transmission electron microscope? We can able to see dislocations. You can see dislocations are so tiny. You can imagine that can be seen through transmission electron microscope. Some people may ask how we can able to see dislocations. The answer is by using transmission electron microscope. We can see high resolution image of non-equilibrium microstructures in steel. Here I have a question. Do you remember what kind of non-equilibrium microstructures we have in steels? Can you name them some? Can you name a few of them?
Benite, martensite.
Very good. Who have answered? Pranav. Pranav, remember the things. This non-equilibrium microstructure forms by non-equilibrium cooling. That is very fast rate of cooling, right? Very good. We can able to see benite. We can able to see martensite. We can able to see Widmanstätten ferrite, which are very small in size, very tiny size substances and phase or microstructures. And we can able to see them under optical microscope also. But the problem is what? You cannot resolve them easily. We can easily resolve single plate of benite, single plate of martensite by using TEM. That is very interesting, right? And we can able to see precipitates of nano size. Let me show you the real precipitates. This is my research while I was doing my master's. You can able to see them. I'm switching on the camera right now. You can able to see them. This one. Okay, here. You can just have a look. Just have a look. The precipitates we have. Spherical precipitates, elongated precipitates. This is a cubed shape. This is visible to everyone?
Sir?
Yeah, you can see cubed shape precipitates, some rectangular shape precipitates, and you can just have a look. What is the size of them? It is visible to size?
Sir?
It is in the nanometer size. You can imagine very nanometer, you can 10⁻⁹ meter size precipitates can be obtained. We can able to see them through transmission electron microscope. You can able to see the dislocations. You can see these are dislocations. Many dislocations are here. Here also you can able to see the dislocations. See, dislocations are pinned by. Can you people tell me how dislocations are pinned? By the small precipitates. The small precipitates have pinned the dislocations. And just look at the upper images. And this is a very beautiful image of a precipitate sitting along the grain boundary of, or sorry, lathe boundary, martensitic lathe boundaries, right? Okay, anyways.
So some are requesting to join.
Okay. So now you people understood up to this point that with the help of microscope, we can identify these things, right? So now what is the motivation of this? What is the, why we are looking at these things? Obviously, can anybody tell me why we are looking at these things? Just use your mind. What help you'll get after that?
Metal characterization.
How we are doing metal characterization, very good. So what is the need of that? Why we characterize the material in this form using optical microscope or scanning electron microscope or transmission electron microscope? What is the need of that?
Can do further researchers on basis of the results.
Okay, fine. This is very simple. We can, by looking at these features, we can say what is the property of a material, right? Am I wrong or right? You can easily say what is the property or what is the behavior or what is the performance of a material in the real situation, or what has happened, why there is a failure, right? Why there is a failure. So that means the properties or the performance of a material can be determined with the help of microscope. How? By looking at these features. Everybody understood now? So you understand how important these microscopes are, right? So now I'll move to some images, real images. You can just see. Can you people tell me which image is this? What is it showing? This is an optical micrograph. This is also an optical micrograph. Optical micrograph means optical microstructure. By using optical microscope, we have got this image. Yes. What is this showing? Can you tell me?
Magnetic steel.
Which steel? This is showing perlite. You people have forgotten everything. These are lamellar structures. Just look at this image. These are lamelles, right? Ferrite and cementite. Ferrite and cementite. Perlitic colonies are present. So this is. Can anybody tell me what is? You can able to see what here? You can able to see grain and grain boundaries. Yes or no?
Yes, sir.
Right.
Yes, sir.
So can anybody tell me how grain boundary is visible clearly here? What has happened here?
Sir, ferrite.
Etching.
Etching. No, I mean how these
So each
grain
and
boundaries are visible. Suppose this is a perlite again. Perlitic colonies is present. Here perlitic colony is present, but the grains are not clearly visible. But anyhow, it is somewhat visible. But it is clearly visible because some pro-eutectoid phase has formed along the grain boundaries. Yes or no? Do you remember the pro-eutectoid phase?
Yes, sir.
Pro-eutectoid ferrite and they basically nucleate along the grain boundaries. Finally, they cover along the. These grain boundaries are called what? Anybody remember the name of these grain boundaries? All the things I have taught in you in physical metallurgy. This is called prior austenitic grain. To remember those things. Prior austenitic. Prior means which has already. Why? Can anybody tell me why it is called prior? The grain boundaries, it is okay. Why it is prior? Because transformation starts from where? Right? Other phases. Remember that?
Yes, sir.
Parent phase is always an austenite, and austenite may transform into perlite, it may transform into some ferrite, cementite, like that, right? So since initially austenite grain is there and grain boundaries is there, and transformation has happened, some perlite has formed and some eutectoid phase has formed along the grain boundaries, right? So eutectoid phase along the grain boundaries help us to identify the grain, size of the grain. Okay, this is an can you people tell me what is this image showing? This is an scanning electron microscope image. What is this? Again perlitic structure, right? Alternate layer of ferrite and cementite. Darker and lighter, right? But this is, but can you people tell me why there is a much difference? What is the difference between them?
Electron
magnification.
Magnification, yeah, one part is magnification, but what is the important part? Just look at here. Here resolution is good, right? You can easily resolve one plate of ferrite and cementite, but it is very difficult to resolve here, right? You understood now? These are clearly visible, yes or no?
Yes, sir.
Right. They are very thin. Ferrite and cementite are very thin. You can easily resolve them into one plates, right? Okay, these are the images of transmission electron microscope. So this is a martensitic plates. Or lathe of martensites, not plate exactly. A plate, you can say, because if you really look into the three-dimensional structure of a benite or martensite or Udman-Stratton ferrite, or are plate shape. They are plate shape basically.
sir, hello.
Yes.
ଏଟା ରଙ୍ଗୀନ କାଇଁ ଦିଶୁଛି ବୋଲି?
Sorry.
ମାନେ ଏଟା ରଙ୍ଗୀନ କାଇଁ ଦିଶୁଛି? ଯୋଡ଼ା
This one.
ହଁ
This one because of etching only, because of etching and because of light only. Your light source is the normal light, ordinary light. That's why.
ସେ
But
ହଳଦିଆ
here you are using an electrons. That's why it is not visible. This is the fault of the light and the microscope.
sir ହଳଦିଆ region
Haldia reason, this is same. I mean, suppose this dark portion are cementite, this lighter portion are ferrite here. or you can say this complete dark portion are perlite. Actually, in the real situation, this complete dark portion are perlite, having alternate layer of ferrite and cementite, right? So darker one is the complete darker one is the cementite, and lighter one is the ferrite. So here lighter one is the ferrite here. Okay, this is a lath of martensite, and this is a bright field image. This is a dark field image. Anyway, but these are precipitates. These you can say M2366 precipitate. This is a precipitate of chromium, basically chromium, iron, molybdenum. These are of nano size, basically. Like as I told, I've shown you some figures. You can able to see them using TEM carefully. And these are dislocations. Dislocations are also very fine, but still you can see them by using TEM. Okay, fine. You got the things. Now, this is our real thing. Microstructure, structure, property, correlation. I think you people have remembered this linear relationship. Can anybody remember the linear relationship between processing, structure, property, and performance in material science?
Yes, sir.
What is the relation? Can you people tell me quickly? If you change the processing, you can change the structure of a material, right? So material structure can be affected by processing, how you are processing the material. So different processing will give you different structures, or you can modify a structure of a material by doing different kind of processing, by choosing different routes of processing. Similarly, if the structure will change, the property of a material will change, right? So property is affected by this change in structure. Finally, what happens? If the properties will change, obviously the performance will change. Performance may increase or decrease, depend upon the properties. If the properties increase is good, then performance is good, obviously. So this is a linear relationship, right? So performance is affected by properties, properties is affected by the structures, and structure is affected by processing.
Hello,
I
sir.
think it is good. Yes? Sorry, can you please be louder?
ପଛ ଇମେଜଟା ଦେଖିବେ ଏଠି
Okay, this one.
ନାଇଁ ସାର୍ ଯେମିତି ଡିସଲୋକେସନ ନଥିଲା ହଁ ସାର୍ ମାନେ ଅପ୍ଟିକାଲ ମାଇକ୍ରୋସ୍କୋପରେ ଦେଖି ପାରବା ନାଇଁ ଡିସଲୋକେସନ
No, never.
ସାର୍ ଯେ ଏଟା ମାନେ ପ୍ରାୟ 1 ମାଇକ୍ରୋମିଟର ସ୍କେଲରେ ଅଛି ତ ମାଇକ୍ରୋମିଟର ସ୍କେଲ ବି ଦେଖି ନାଇଁ ପାର ଅପ୍ଟିକାଲ ମାଇକ୍ରୋସ୍କୋପରେ micron size things you can able to see, but nano size. तो सर डिसलोकेशन वन तो 1 माइक्रोमीटर ଅଛି କେମିତି ଯାଇନା
1 micrometer? Where 1 micrometer? This is a scale bar. You are getting confused. This is a scale bar. Magnification is different, but scale bar is different. Scale bar means total entire length is of 1 micrometer. You understood now? But this is 1 micrometer. The substance present in that is not 1 micrometer. You understood now, I think.
Sir.
This is 200 nanometer. That means from here it is 200 nanometer.
yes sir
But you are able to see a very nanoparticle size, M23C6. Maybe it is some 100 nanometer, maybe, or 50 nanometer, like that. So this is 1 micrometer, but the dislocation size is very small compared to that, some nano size. Fine. Okay, anyways, these are some other structures. You can able to see grains, some deformed grains. These are some welding structures. And these are some porosity. You can able to see porosity, as I told. This is one porosity, this is another porosity. Some impurities can be also seen by using optical microscopes. Okay, so this is the relationship. Yes?
Sir, precipitation और dislocation वजह से difference किंतु sir माने हमें देखी पार जो माने पका पकी माने
it is visible. It is clearly visible how dislocation are you can able to see. This is one dislocation. This is one dislocation. This is one dislocation. This is one dislocation. Many dislocations are there. Dislocation line actually. These are dislocation line. You understand now?
Sir, figure C रे sir हमें किंतु माने इटा precipitation बोले जान लो. Heta sir doubt actually.
Okay, how you can identify? Okay, you have to do EDX. There is a method called EDX, in energy dispersive X-rays, or energy dispersive spectroscopy, that is called. Some people call EDX simply. energy dispersive X-ray or energy dispersive spectroscopy, right? What it do? There is an attachment with the microscope. In this microscope, there will be an attachment. So you have to do EDX on it. EDX on it means you have to take the composition of this one, right? If you take the composition, you will getting M23C6. That means this M23C6 means it will show carbon. C means carbon, M means some metals. It may be molybdenum, chromium, and iron, right? So it will show some peaks. Let me show you some index result. Otherwise, if you are getting confused, let me show you. Okay, I'll show you later. Otherwise, I have no much time here. You understand? That means you can easily determine the composition of that particular particle. You can see this is a matrix. This lighter portion is a matrix. In that matrix, some precipitates are there. This is one. This is one. This is one. This is one. Right? You understand now? And the sizes you can imagine. This is scale bar is 200 nanometer. That means size will be very smaller. The size is very small. Only precipitate size are very small. Right? You can able to see. You can measure the composition of that. Once you determine the composition, you can confirm this is a precipitate of M23C6.
Yes, sir.
You understood now? Okay, let me. Okay, I have. Okay, no, I don't have right now. Anyways, so now you people have understood. So finally, these two are important: the green and the red. So that means what I have written: by changing the microstructure or microconstituents of a materials, the properties can be altered, and that results in change in performance. So performance of a material depends upon the properties, and properties can be altered by altering the microstructure. You can also write by altering the microstructure and nanostructure if nanostructures are there. Nanostructure means this precipitates. If you want, you can write, no problem. Nanostructures also. Nanostructures and microconstituents also, and microconstituents. Microconstituents means ferrite is a microconstituent, martensite is a microconstituent, you can say. Perlite is a microconstituent. Perlite, ferrite, which are the microconstituents present in the steels basically, not other materials. So you people understood now? That means these things and these things are microstructures and nanostructures. By altering them, we can alter the properties, or we can change the properties of a material. Then if the property will change, then performance of a material will also change. Depends upon how property is increasing, the performance will increase. Now, same thing I will discuss here. Just look at this one. Properties of a crystalline material affected by. What are the things which will affect the property of a crystalline materials? So I have mentioned here, that is microstructures and microconstituents, right? Microstructures, if you change the microstructure, the property will change. If you change the microconstituent, the property will change, right? So now, what are the microstructures? The microstructures are what? The microstructures are the things which we can able to see under a microscope, right? Already we have seen them, as I show you these things, right? Now, first one is the type of phase or mixture of phase present. Different phase have different characteristics nature, right? This is the first one. So that means after looking under a microscope of a material, you have to identify what are the different phases present. A single phase is present or multiple phase is present. Multiple phase will present means it's a mixture of phase maybe, right? So that, and you understand individual phase have a individual nature, property. For example, if ferrite will be there simply. So what will be the property? Can you people tell me? Already you have studied your physical metallurgy and the mechanical metallurgy, that is deformation behavior. So ferrite is of what nature? Tell me quickly. Ferrite is of what kind of nature?
Ductile.
Ductile, very good. That's all, very good. It is a soft phase, ductile phase or soft phase. So I'm writing the examples if you want. Right now I'm writing here ferrite. Ferrite is soft. Tile. That means you understand if your steel is containing lot of ferrite or only ferrite matrix, that means it is having high ductility. It has a high elongation. You can deform that particular steel to a large extent, to very, very small cross-section area. You can deform it, starting from a very thicker plate to very thinner plate, right? It is okay. Similarly, if I have martensite, I have martensite. So what is the nature here?
High strength.
Hard.
Hard and brittle sometimes. And brittle. Hard and brittle. So hard and brittle means, you understand, it will increase the what? It will increase the strength, right? It will increase the strength, it will increase the hardness, and sometimes it depends upon the, okay, fine. As example, suppose I have tempered martensite. Tempered martensite. What is the advantage of tempered martensite? It is having good toughness.
Ductility.
Toughness. Because tempered martensite is somewhat ductile as compared to that of the original martensite, parent martensite. Good toughness.
Sir, ଆପଣଙ୍କର voice ଟା
Strength.
କଟୁଛି sir.
Yes.
ଆପଣଙ୍କର voice ଟା କଟୁଛି sir.
Am I audible to others, or you are finding difficulty?
No, sir, you're audible.
Audible.
Yes, I think you have some problem, because my
Yes, sir,
internet
audible.
connection is good. You do one thing, you just leave and again join. That will be fine. You can able to listen the voice. So if I have tempered martensite, then it is having good toughness, good strength, and some ductility also, right? Similarly, if I have a benite, if you remember, if I have benitic phase, then, or benitic microstructure. So can you people tell me what is the nature of the benite?
High wear resistance.
High toughness.
First is the high toughness. Very good. Good toughness or excellent toughness. You can add excellent. Excellent toughness.
High corrosion resistance.
Corrosion resistance. How corrosion resistance will be there? Can you justify how corrosion resistance will come?
Sir, honest steel अपेक्षा better था.
Benite is a micro constituents, or it is a microstructure simply, or it is a phase, or it is actually not phase. It is a mixture of phase. Ferrite and cementite is there. But how it will affect the corrosion property? Corrosion property will be affected the moment you add some alloying elements like chromium. In case of stainless steel, you are adding chromium and nickel. Chromium and nickel, they form a oxide coating on the steel surface. Chromium oxide layer, very thin and adherent chromium oxide layer will form on the steel. That will provide corrosion resistance. But how benite will provide? Benite will decide the strength or mechanical properties. You got the point now? It is okay up to this?
Yes, sir.
Excellent toughness, and strength. Right. Similarly, suppose I have perlite. Then perlite is a mixture of phase again. Benite is a mixture of phase. Perlite is a mixture of phase. So if I have perlite, then what kind of property it has? Good strength, good toughness, good strength, good toughness. These are the things, right? Because perlite is a mixture of ferrite and cementite. Cementite, if suppose I have cementite, more amount of cementite. Cementite nature is what?
Hardness high.
Very, it is completely hard and brittle. Hard and brittle. It is a completely hard and brittle. Do you remember why cementite is hard and brittle?
Higher amount of carbon.
Higher amount of carbon. Okay, 6.67. That is one part. Single phase, no? So how you can just... This is very simple, because do you remember the structure?
Sir, complex orthorhombic.
Complex orthorhombic, very good. Do you remember? Complex people remember the sleep?
Difficult.
Difficult, yes, difficult. Sleep is happening means plastic deformation is happening easily. If sleep will be difficult, then plastic deformation will not occur, right? So because of complex orthorhombic structure, it has a very complicated crystal structure, and lot of carbon atoms are present in that. So what happens? The sleep is very difficult in the cementite. So in sleep will be not there, plastic deformation will not happen. So it is a very hard and brittle, basically. So you understand, cementite is there and ferrite is there in case of perlite. Perlite is a mixture of phase, right? So it provides you two things: soft phase and combination of soft phase and hard phase. So good strength and good toughness, right? Benite is also a mixture of phase. You should not be confused. Benite is also a mixture of phase. It is mixture of again ferrite and cementite. But do you people remember what is the difference between perlite and benite? Both are the same mixture of same thing. Let me see, anybody remember that? Yes.
Sir, grown size is slightly smaller in benite.
Sorry.
Grain size is smaller in benite.
Okay, fine. Yes. In case of benite, the benite are very fine microstructure. But perlite is
Lower benite.
somewhat coarser, bigger size grain. Okay, very good. That is one part. But benite is actually a plate shape. You can look at the images in the physical metallurgy. You can, if you want. These are plates of ferrite and if you remember, the perlite morphology is lamellar, right? It looks like alternate layer of ferrite and cementite. But benite is not like that. Do you remember how benite looks like? There are two types of benite, upper and lower.
Yes, sir.
Plate-like structures, plate-like perlites, and in between there are cementites between the plates.
Okay, you have this is not exactly right, but if you remember, we have plates. Those plates are of ferrite plates, and distribution of those cementite will decide it is a upper benite or lower benite. If distribution of cementite is in between the ferrite plate, right, like a sandwich, that is a upper benite. Lower benite is distribution of cementite will be somewhat inside the ferritic plate and somewhat in between the ferritic plate. That is called lower benite. Now I think you recall those things. You can check your class notes if you want. Anyways, so you now you people understood now how properties is changing by changing the micro constituents and by changing the phase. It is okay now up to this?
Yes, sir.
So different phase or different mixture of phase will decide what is the behavior of a material, right? So that means these things can be obtained by looking under a microscope only, right? Whether it is ferrite, whether it is benite, whether it is martensite, you can able to see under a microscope. That's all. Second one is distribution of phase. Second one is, this is interesting, distribution of phase. So distribution of phase means position of phase inside the grain and grain boundaries. That means if a phase is there, then that particular microconstituents or that particular phase is present where? Inside the grain or along the grain boundaries or somewhere else. That also affects. Can anybody justify that? The hint is cementite. Let me tell you about cementite. Can you justify now how the position of cementite will affect the property? I have told you this in the iron carbon phase diagram. I remember that. Just few minutes before I have talked to you about this, if you remember, proiectoid phase. Where proiectoid phase formed and where and what happens to the proiectoid phase later with time. Cementite, if you remember, if you are talking about hypereutectoid steel, do you remember what is an hypereutectoid steel? How many of you have remembered this one?
Yes, sir.
What is
Yes, sir. More than 0.8% of carbon.
very good. If the carbon weight percentage is more
No, sir.
Never.
Perlite plus
Light and cementite.
Proeutectoid cementite. Perlite plus proeutectoid cementite. If the carbon weight percentage is of 0.8 weight percent, that is called eutectoid steel. If you have a eutectoid steel and you are doing equilibrium cooling from high temperature, you will get only 100% perlite. Right? But if you have a hypereutectoid steel, can you mute yourself? Mute. If you have a hypereutectoid steel, then do you remember the iron carbon diagram? The extreme part, right side part is cementite, and now left side part is perlite. So that means in hypereutectoid steel, you will have perlite plus proeutectoid cementite. You understand now? Similarly, if you have a hypoeutectoid steel, what is the equilibrium phases at room temperature?
Ferrite plus perlite.
Yes, very good. Ferrite plus perlite, because the left extreme is your ferrite and now right extreme is your perlite. So it is the ferrite plus perlite, or basically it is called perlite plus proeutectoid ferrite. You should not forget this one. Proeutectoid word is important here. Anyways, so your distribution of phases. Distribution of phases means I told where the phases are getting distributed. Suppose in a hypereutectoid steel, suppose for example this one. So suppose consider this is an hypereutectoid steel and this is the cementite network. This is a network of cementite forming along the grain boundaries. So this kind of structure is good or bad? The network of cementite along the grain boundaries is good or bad for the property of steel?
Bad.
Bad. How? Can you justify that?
Sir, जो जगह उड़ा ferrite plus सेटा soften है जो grain boundary टा soften थिबो.
I am talking about network of cementite. Cementite is a very hard and brittle phase. So how it is a soft phase? Yes, can anybody else? Because once the crack will form, listen it carefully, once the crack will initiate, where the crack will initiate? Which one is the brittle phase? So cementite is the brittle phase. So crack will initiate along the grain boundaries and it is a continuous network. So what will happen? What will happen then?
Crack propagation will
Crack
be
will
more
propagate
easy.
along the grain boundaries and it will be easy way. Crack will find a easy way to propagate and finally your material will get failed. Okay, what is the solution of this? What is the solution of this? Can anyone tell me what is the solution of this? We have to prevent what? We have to prevent the formation of what? The network of cementites, right? We have to prevent the formation of network of cementite, because once network of cementite will form, you cannot avoid a crack if it's formed along the grain boundaries, right? So that can be done by just normalizing. You do normalizing. If you remember, normalizing means air cooling. You take the steel to the austenitizing temperature. Then from austenitizing temperature, you cool the sample in the normal atmosphere. So normalizing will take place. Normalizing will take place means it is a faster cooling. So that means the cementite which is formed along the grain boundaries will not get time to grow along the grain boundaries, right? So it will remain as a small particles along the grain boundaries. That is okay. Or you can do spheroidizing heat treatment. There is okay, I will discuss that. That is one part, spheroidizing heat treatment, where what happens, this network of cementite will become spheroid, spherical size particle, and it will uniformly distributed throughout the materials, right? So this is the so now you understood now distribution of phase is how important and how it affects the property of steel or material. This is okay now?
Yes, sir.
Then we'll move to relative proportion of phase. Relative proportion of phase means suppose you have two different phase. Suppose you have two different phase. Suppose you have you have perlite, one mixture of phase, and you have ferrite, another phase. Perlite is a mixture of phase. You can consider that is one, and there is a ferrite. So relative proportion or amount of each phase or in a phase mixture is important. So that means if you have more amount of ferrite and less amount of perlite, so property will be what? It will be more ductile, obviously. But if just opposite will happen, if the ferrite percentage will be less, perlite percentage will be more. So obviously it will become more hard and more stronger. Ductility will go down. So relative proportion you understood now?
Yes,
It is
sir.
okay now? Very good. Now shape of phase. Now shape of phase is also important. So it is a spheroid shape, or it is an elongated shape, or it is a plate shape, or it is a network kind of shape. So many shapes are there. It also affects. Okay, tell me one thing. Suppose you have a cementite and that is of sharp edge. The cementite phase is present and cementite is having sharp end. And in another microstructure, same steel, you have spherical shape of cementite. So which one is good?
Spherical.
Spherical one is good. How? How you can justify that? Already you have studied about the mechanical metallurgy, that is your deformation behavior. You have heard about the stress riser, stress concentration sites. I told you in IPM, I remember.
The area increases in spheroid.
Okay. So
So
what will
stress,
happen?
so stress concentration is more in pointed one.
Very good, very good. See, when you apply a load, so we are talking about stress because force per unit area, right? So when you are applying a force on a material, that is suppose force per unit area, that is stress. So distribution of stress should be uniform, right? If the stress distribution will be non-uniform, and if the concentration of stress is higher at a particular point in a material, the crack always initiate from there, because that is a stress concentration site. The concentration of stress is high at that point, right? So that means if you are taking spheroidized cementite, then it is a spherical particle. So distribution of stress is uniform. You can understand basically. But if you have a plate kind of cementite or a needle shaped cementite, the both end is having sharp end. So that will act as a stress concentration site, or that will act as a stress riser. So where the stress concentration will be more. So crack will initiate from there. You understood now how shape is important, or how shape will decide the properties of a material? The any moment you find difficulty, just ask me, I will repeat it. It is okay up to this?
Yes, sir.
Then we'll move to the presence of second phase and its size, shape, and distribution. Second phase, do you remember what is the second phase? What is the second phase?
Precipitate.
Precipitate. Who told? Rameshwari. Yeah, she remember. Precipitates are second phase. So if you remember, precipitate forms when there will be a limited solid solubility. That means suppose you have a steel and you have added some chromium, for example, right? You have added large amount of chromium into the steel. So steel, it may be a ferritic steel, it may be a martensitic, depend upon the microstructure, right? Suppose it is a ferritic steel. The matrix is ferrite, but the chromium is not so much soluble right now, right? And you have carbon in it. So what will happen? Can you tell me?
Chromium carbide will form.
Chromium carbide will form, right? The chromium will start reacting with the carbon because chromium solubility is decreasing. So chromium react with carbon to form chromium carbide, and chromium carbide is a precipitate. So precipitation will start. It will form basically along the grain boundaries. Precipitate. Precipitates. Some precipitates you can call intermetallic phase. Intermetallic phase. These are the examples. So these precipitates are also helpful for increasing the strength of a material. If precipitates will form along the grain boundaries, they will pin the grain boundaries. So when they will pin the grain boundaries, the grain growth will be prevented or will be restricted. So grain growth will be restricted means the strength will be more at high temperature also, right? Their shape is also important. Size is important. If it is a bigger size precipitate or smaller size precipitate, basically we want smaller size precipitate and more uniform distribution of precipitate. The precipitate should be more uniformly distributed. That is good actually. But if it is not uniformly distributed, that is a problem again. Similarly, size bigger or smaller, size and okay, then size of the crystal and grain. You remember, right? So we have what kind of size basically? In technical term, what we call grain size is? Which kind of size we have?
So coarser grain and finer grain.
Coarser and finer grain. Very good. Coarser. See. Coarser and finer. Which grain, which kind of grain will provide more strength?
Finer.
More grain boundary, more hindrance to dislocation motion. More number of grain boundaries, so that more hindrance to dislocation motion.
Yes, very good, very good. Coarser grain means, if you remember, the grain will be coarser one. That means less number of grains will be there. Less number of grains means less number of grain boundaries. Less number of grain boundaries means less number of obstacles before the dislocations. So dislocation can easily move. But if you have finer grains, more number of grains will be there. More number of grains means more number of grain boundaries will be there. More number of grain boundaries means more number of obstacles before the dislocations. So dislocation will be getting stopped randomly, or frequently it will get stopped by the grain boundaries. So obviously that is strength will be more. So this is the way. So that by looking at the okay, we'll move to the
Sir, I have a small question, sir.
Sure.
Sir, is it the introductory class or we have started any particular
No,
topic?
this is the class I have started already.
Okay, because I have lost off the track already.
Okay, sure, no problem. See, when the class will be over, you can ask me.
Okay, sir.
I will again show you the slides quickly, once again, so that you can take screenshot of that. Now, types and density of lattice defect. If you remember, we have talked about many kind of defects. So most important defect in our material is which kind of defect? Do you remember? Which defect is most important? Already I have written over here.
Dislocation.
Dislocations, yes. Dislocation is which kind of defect? It comes under which category of defect?
Two-dimensional
defect, or it is one-dimensional?
Two-dimensional.
One dimensional.
Are you sure two-dimensional?
One dimension.
It is one-dimensional defect. It is a linear linear defect. Linear defect is always in one-dimensional. It is a line, no? It is moving from one direction to another direction in a single direction. So how it will be a two-dimensional? It is a linear defect, line defect, some people call, right? So it is a linear defect. So dislocation, you understand. So density of dislocation is very important. If the density of dislocation will be more and more in the material, then the strength will increase in the material, right? If dislocation will be less, then it will be a what? It will be basically a soft material, right? So that do you people have heard about annealed substance or annealed material and cold walled materials? Have you ever heard about this?
Yes, sir.
Sir.
Very good. Annealed and cold walled. So in which material you got high dislocation density?
Cold walled.
Cold walled. Very good. Why?
Sir, because at low temperature, when we try to deform it, many dislocations get generated.
Very good. You remember that. Very good. So basically what happens? Annealed material means it has undergo which process? Annealing process. Do you remember I have taught you annealing in a very good, nice way? After cold working, we have to do annealing of that. Annealing of what are the different stages of annealing? Do you remember?
Yes, sir. Recovery.
Very good. Recovery.
Recrystallization and grain growth.
Then grain growth. Very good. So annealing will go like this. First recovery will take place, then recrystallization, then grain growth. So during this, what happens? Dislocation, annihilation occurs. Annihilation means they will get disappear from the material, right? But during cold working, large amount of dislocation will generate. Do you remember what is the source of dislocation? How they generate? What is the source of dislocation? How dislocation generates the material? Frank Reed source. Do you remember that now? Frank Reed source.
Yes, sir.
Frank Reed source. The dislocation is moving, then it is getting pinned at both ends. Now you are recalling the figure.
So that is multiplication of dislocation.
Yeah, obviously dislocation means what? The dislocation density is increasing in a material.
No, sir, but for that we are giving some kind of stress.
Obviously, you are doing cold working. Cold working means what? We are applying a lot of stress into the material so that it will deform. right?
Yes, sir.
So that is the stress coming out. That is the thing, the stress will come out, right? You are doing cold working. You are applying large amount of load onto the material. Okay, you remember that, right? Dislocation is moving, then it will come in contact with two second phase particles. Then the second phase particle will pin up the dislocation at both ends. Then you are applying more stress. The dislocation cannot move because it is getting pinned by the two particles at the both ends. Then it will become what? It will bulge out slowly. And finally, it will form a loop. And finally, this loop will come in contact with one another. So the moment it will come in contact with one another, a new dislocation will generate. But initial dislocation will get pinned up there. Similarly, many dislocations will generate in the materials. So when lot of dislocations will be there, what will happen? They will start interacting with one another, right? They will get tangled up, and the dislocation movement will be get restricted. So that phenomenon is called what? Do you remember that? What is that phenomenon called? When the dislocation movement will get restricted, it will become sessile.
Dislocation pile-up.
Dislocation pile-up, that is a different thing. Pile-up means they are moving towards the grain boundary and they will be stopped by the grain boundaries. That is the pile-up along the grain boundaries. No, that is the strain hardening phenomena. You people have forgotten everything. Just go through your IPM class, at least. IPM lecture note. If you want, I'll send you, or your junior will send you the recent lecture note, right? If you want that, you just tell me. I will send you otherwise. Just look at the stress strain curve. Why strain hardening is occurring just after the yield point. Do you remember strain hardening phenomenon? Okay, I'll show you one day. Otherwise, I will otherwise recall those things in next class, perhaps, so that it will be easy for you. Okay, next is casting defects. Casting defects, you understand porosity is a casting defect. That porosity means it may be a gas porosity, gas pocket like that. Gas pockets. Some hairline cracks. Do you have heard about these things? Have you ever heard about these things? Hairline cracks, gas pockets.
Yes, sir. Gas pockets.
Blowholes, surface blows.
Yes, sir.
Okay, very good. You have heard, no? Blowholes. These are formed during casting, when you solidify a liquid metal in the mold. During the solidification process, some gas will get entrapped, right? Some gas will get entrapped. What kind of gas may be? It may be oxygen, it may be nitrogen, it may be hydrogen. These are the gases. If they will get entrapped and solidification has happened, it will lead to gas porosity or pockets or hairline crack. Hairline crack often basically in case of hydrogen. Because hydrogen is very thin, very small size particle, it will come out and it looks like hairline. Yes. Blowholes and gas pockets are this due to the evolution of oxygen, basically. So these are defects, right? So now you people understood how properties of a crystalline material is affected. Up to this, you have no doubt. So this is the end of the. Okay, fine. Last topic I am moving into this. Techniques, different processing to improve the properties or performance of a material. I have shown you this one: processing, structure, property, performance. Performance is affected by property, properties is affected by structure, and structure of a material is affected by processing. So now we are discussing about that one: processing, different processing or different technique of processing to improve the properties or performance of a material. So these are the three important topics. One is the plastic deformation. That is, you can do cold working and hot working, right? So this is one of the technique by which we can enhance or increase the property or performance of a material. Can anybody remember the difference between cold working and hot working?
Yes, sir. Recrystallization temperature.
Recrystallization temperature will decide, yes. So tell me clearly, yes.
Above recrystallization temperature, hot working. Below recrystallization temperature, cold working.
Yes, very good, very good. So what is the range of recrystallization temperature?
0.4 to 0.5 TM.
Okay, fine, yeah. If you go through various literatures, some people call 0.3 to 0.5 TM. TM means melting point or melting temperature in Kelvin. 0.3 to 0.5. Or some textbook have written half of the melting point is the recrystallization temperature. Okay, what is recrystallization? Anybody tell me what is recrystallization?
temperature at which strain-free grains are produced.
Very good. The temperature at which the new strain-free crystals. Re means again, crystallization means formation of new crystals or formation of new grains. That's why name is recrystallization. So formation of new strain-free grains. So where they start forms basically? In which area of a material they forms basically?
Grain boundary.
Basically, yes, where 2 to 3 grain boundaries are meeting, right? Because there is a high energy portion, so high energy regions. Basically, if you carefully look, when we deform a material, some grains are more deformed, some grains are lessly deformed. So more deformed grain means more number of dislocations. Less deformed grain means less number of dislocations. So more deformed grain will fast recrystallize. And this grain boundary will migrate towards the less deformed grain. Slowly, it will consume all the dislocations with time. Okay, so in which case you'll able to see recrystallization, hot working or cold working, basically, without doing
Hot
any
working.
other treatment. Yes, in which case?
Hot working.
Hot working, very good. And that kind of recrystallization is called what kind of crystallization? Dynamic. Right? Dynamic. It is deforming, new crystal is generating. Again, deforming, new crystal is generating, right? Dynamic. Okay, anyways, you understand. So this is okay, can anybody tell me fine what is the conclusion of this? How plastic deformation affects the property and performance of a material? Just tell me in one sentence or in 2 lines. I'll write here. Tell me. I've told you everything about cold working, hot working now. So cold working will lead to what? Tell me Jaldu, quickly. Cold working will lead to
High dislocation density.
yes. So high dislocation density leads to finally
High strength.
strain hardening. Strain hardening phenomena. Due to reason is high dislocation density. High dislocation density. Right? You understand? That means if you do cold working on a material, you can increase the strength, you can increase the hardness. Right? This is the one of the way to change the property of a material. So suppose your father will come and your father will tell that, son, you have studied metallurgy now. I have a metal, but which is very soft. So what I can do? Tell him, just go and strike it with hammer. Give a strike with the help of a hammer. The moment you are hammering the materials, so what will happen? Huh? What will happen? Just tell me quickly.
More number of dislocations.
It will deform plastically. It will deform plastically, and once it will deform plastically, more number of dislocation will generate, and more number of dislocation will generate means the dislocation moment will be restricted, so strength will increase automatically. This is a simple way you can do that, and your father will get impressed, obviously. Okay, fine. What about hot working? Suppose you are doing hot working, so how the property is changing? Can you tell me? Hot working will leads to what? Just few minutes before I told. Leads to which phenomenon?
High strength.
High strength, right? Very good. So if you're talking about defect, then it brings ductility. But if you're talking about the size of the grain, it brings strength. You understood now? This is one of the way. So second, the measure one, okay, next one is the changing composition. If you change the composition of a pure metal, you can increase the properties. You can change the performance of a material. Can anybody give me a best example of here? Tell me quickly. A pure metal and steel and right? Pure iron versus mild steel. I can write that. Okay. Pure iron is very soft, ductile, malleable. It has high formability, workability. But once you make mild steel, that means you are adding carbon into the iron, right? The strength will increase, the ductility will decrease, the toughness will increase. You understand now? So by changing the composition, you can change the properties of a material. Any other examples? Any other examples? Suppose I want to compare mild steel with some other kind of steel. Tell me. Mild steel versus stainless steel. Yes or no? What is the difference between mild steel and stainless steel? How the property will change?
Corrosion
The
resistant.
chromium, presence of chromium.
Yes, presence of chromium and nickel, right? In stainless steel, we have iron, we have little amount of carbon, and we have chromium and nickel, right? So we are changing the composition now by adding chromium and nickel into the steel. It becomes stainless steel. But mild steel means only iron and carbon will be there. So what kind of property will be enhanced? Corrosion resistance. Best example. Chemical properties. Corrosion resistance will increase. It will not get easily corroded at high temperature also, right? But mild steel will easily corrode. Any other property? The strength will increase, the hardness will increase. Because which kind of mechanism? Do you remember how the strength and hardness will increase? Which kind of mechanism? Just remember. The hint is carbon is which kind of alloying element, and chromium and nickel are which kind of alloying element? Which category of alloying element?
Carbon is interstitial.
Very
element.
good. Carbon is interstitial alloying element. What about this stainless steel? I mean chromium and nickel?
Substitutional.
Substitutional. So which kind of strengthening will be there? Substitutional strengthening or solid solution strengthening. It form a solid solution. Do you remember these things from physical metallurgy? So we'll form a solid solution. Solid solution always increase the strength of a material due to elastic strain in the body. Okay, fine. So you understand. So finally, the interesting part is the heat treatment. So there is another technique and the processing called heat treatment. So heat treatment may be thermal heat treatment, where it involves only high temperature, heat. Nothing else will be there. Chemical heat treatment, but chemical heat treatment involves two things: high temperature as well as some chemicals will be required for chemical heat treatment. And there is a thermomechanical heat treatment. Thermomechanical heat treatment, can anybody guess? The name is same. This one and this one.
Heat plus mechanical work.
Very good. Heat plus mechanical working. High temperature plus mechanical working is needed. So heat treatment may be classified as thermal heat treatment, chemical heat treatment, and thermomechanical heat treatment. So heat treatment is a very good technique or very good kind of processing which can remove this one or which can remove this one, right? You can enhance the properties of a material or you can enhance the performance of a materials just by using heat, just by using furnaces. How to do heating? Just by using different furnaces. Have to use high temperature, high and medium temperature furnaces. We can do heat treatment on the materials, right? But in details, we'll start from the next class or next to next class. This is an introductory class, but these are very essential. Okay, if you have any doubt, you can ask me right now. I'll clear it.
चैनल और पेस्ट ओपन करें
1 2 3 this is 4. Yes, these are welded images after doing welding and all.
सर लास्ट पेस्ट है ठीक है
Sir,
Yes.
sir, changing a shape of a material, is it a thermomechanical treatment?
Oh, yes, obviously. How you can change the shape? How you can change the shape? We can change the shape by how? Tell me. By doing rolling, by doing forging, or by doing extrusion, or by deep drawing, right? You have heard these terms in your, that is your mechanical metallurgy part. You have studied these things somewhat. Hot rolling, cold rolling, right? So this is the one way you can change the shape. And the important point here, presence of second phase you can also write presence of non-metallic inclusions. Non-metallic inclusions also influence the properties. Non-metallic inclusions means maybe some oxides, some sulfides, sulfides, some silicates present in steels or any materials. The best example in case of steel, the non-metallic inclusion is manganese sulfide. Manganese sulfide. Manganese, if you add manganese into the steel to take care of your sulfur, then it forms manganese sulfide. So it remains as an inclusion sometimes in the steel. It should be removed out, but it is still remaining in the steel in form of a non-metallic inclusions. They are basically non-metallic inclusions are very hard phase. They are basically very hard phase. Hard phase. Hard phase means they will not undergo deformation. While you are deforming, they will not undergo deformation. So what will happen? Can anybody tell me if non-metallic inclusions are there in a steel and you are deforming the steel, what will happen? Just around the non-metallic inclusions? Stress concentration will be more? Yes or no?
Crack will.
Stress concentration will be more because crack may initiate or not, that depend upon the amount of stress acting on it, right? But if you're deforming, the steel will easily deform. It is a ductile substance. But these non-metallic inclusions are very hard. They will not deform easily. An oxide, you cannot deform it much. Sulfide. So what will happen? Around the non-metallic inclusions, lot of strain will generate, right? Lot of strain will generate. So that may be helpful in the crack propagation or initiation. Or sometimes it is also helpful for recrystallization processes. Some recrystallization also happens along the boundaries of these materials because due to presence of high strain around them. Okay, you have any doubt right now? Okay, can you people tell me why porosity will affect the property? How porosity will affect the property? Can you tell me? If a porosity will be there, how it will affect the property?
The density will decrease.
Density will decrease. That is okay, but I am not talking about density. Density property, forget about density properties. Strength, I am talking about strength or something else. Porosity means it is a gas pocket, I told, or it's some space is present.
So while
more porosity, strength decreases.
More porosity will decrease in strength. Why? Because that will act as a crack initiation point. Why crack initiation point? Just imagine you have a block of steel. I have given you a block of steel, and at the center of that block of steel, a porosity is there. So if you apply a tensile load, what will happen? You are applying a lot of tensile load on it now. So what will happen? The crack will initiate from the porosity part. Why?
So stress concentration is more.
Yes, very good. Again, the concentration of stress will be very high around that porosity. It is okay. So that means the crack will initiate from there only. The distribution of stress is non-uniform right now. But if a material is having no porosity, then distribution of stress will be good. But if a material is having some second phase particles or some hard phase particles like inclusions, from there the crack may initiate because of high stress concentration or that is called stress riser. Rising of stress rises. Called technical term is stress rises. Okay, you everybody have understood up to this, I think.
Corrosion rate will also increase.
What? Again.
Corrosion rate.
Sorry.
Sir, more porosity, more corrosion rate.
More porosity, more corrosion rate. Corrosion is related to that. How you can call how it is related? I didn't get. See, corrosion. Okay, you have. Oh yeah. You can tell me. Yes. Okay, let me end the meeting and not end the meeting. Let me stop the recording first. Yeah. Tell